Okay, so I'm going to graph this guy. There's the graph of the function. Okay. Now I want to graph the derivative. Look what I could do. I could graph g of x equals f prime of x. And it's graphing the derivative. Okay. How could I use those graphs to see if what I got is correct? What I got for the derivative? I mean, I could do it a couple ways. Like I could literally, there is the graph of the derivative. If I graph what I got for the derivative, it better match that function or I got the derivative wrong. See what I'm saying? Okay. The other thing is let's assume you got it right. Let's assume you got the derivative right. How in the world are you going to find the zeros of that derivative? Obviously, I mean, like that's going to be a pretty tough problem to solve, right? To solve that polynomial equation. I don't want you wasting your time using rational root theorem and using what's the heck's that? I can't remember what the name of that theorem is. I showed you guys about when the sign changes. I can't even think of the name of it right now. But I don't want you spending an hour and a half just finding the zeros of that thing. So what do? You find them graphically. Okay, on those, if it's a cubic or a quadratic or something, that's fine. Then you can find it algebraically. But if it's that big, just get on the graph here. And I'm looking at the graph of the derivative. Let's just find the zeros graphically. They're -7 and 3. Okay, make sense? And then the asymptote here, the asymptote is at a place where the function's undefined anyway, right? Because the function's undefined at, what was it, at +3 and -2, right? So we've got a vertical asymptote here where the function's undefined, so that's excluded from the domain. So the only critical numbers of the derivative are going to be, are the only critical numbers that turn out to be zeros of the derivative are there, right? I can find the zeros of the derivative graphically, right? I've got to take this thing and find out where the function's equal to 0. Well, there's where it's equal to 0 at -7 and +3, right? Yes. See from the graph, we can see that. Now, how would we have solved that equation? What we would have done, like I don't want you doing this, but here would have been the way that if you went through the whole process, and I don't want you to, but if you did, you'd take this function, the derivative is equal to 0 when that function right there equals 0, right? So I'll take 30 seconds and review how we would do it, but again, I don't expect you to. So if I'm asking when that is 0, well, that's a polynomial, right? I could use the rational root theorem. What's the list of all the possible zeros that I could run through and test synthetically, right? The possible zeros would be the factors of the constant, positive and negative factors of the constant divided by the factors of the leading coefficient, which is 1, which is convenient that it's 1. So it would just be all the factors of -189, right? I mean, if I made a factor tree out of 189, well, 189 is divisible by 9, right? Because the sum of the digits is divisible by 9. So it's 9 times 21. So I'm going to get 3, 3, 3, 7. So I get, those are the factors. So what would I choose then? you know, the numbers I would have to test would be x equals plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 9, plus or minus 21. Those are all different factors I could make out of those prime factors. And I would start with the easy ones and just work my way down. I would cross out the ones. And then if I made a synthetic bracket here, what would that look like? I'd have the coefficients along the top, 1, negative 2, negative 36, 162, negative 189. Remember doing this? And then I would just test each of those values and see, like if I plugged in positive 1, well, I'd bring the 1 down synthetically, multiply by 1, and add to negative 2. So that's going to give me 1. 1 times 1 is 1 plus negative 2 is negative 1 times 1 is negative 1 plus negative 36 is negative 37, etc. And when I add all these things up, I would have to get a 0 there, right, for it to be a factor, right? If I was trying to factor this thing to find the zeros. And I would just say it again. Because think about what you do synthetically. I bring the 1 down. 1 times 1 is 1 plus negative 2 is negative 1. These are just the numbers that show up under the synthetic bracket. We do the math mentally to get there, right? 1 times negative 37 plus 162 is going to be some, I'm not going to get 0, right? You can already see this one's not going to work. So I could cross positive 1 off the list and keep going, right? I would end up crossing negative 1 off the list. If I tried 3, let's just show one that works, just so you can see this. Like if I try 3, I bring the 1 down. 1 times 3 is 3 plus negative 2 is 1. 3 times 1 is 3 plus negative 36 is negative 33. 3 times negative 33 is negative 99 plus 162 is 63. 3 times 63 is 189 plus negative 189 is 0. So we hit a winner, right? We hit a winner with 3, and then all we have to do is that and keep going. But now I'm going with a smaller polynomial, right? You get my point? But this is only going to find the rational zeros. If they're irrational, you're sunk, right? Okay. So again, I don't expect you to do that. Okay. Does that make sense? Okay. All right, so here's the couple. Everyone just take a second and look at these, and you tell me if and when you ever want to go through one of these. So that's one. And the only reason this one I think is not a bad one, here's why. And I guess we could just take a second and look at just one little part of this. That's just finding the domain. That's it. Once you find the domain, this isn't very bad. But you got to find the domain. Well, what's the red flag here? The red flag is the square root. What's our rule for even roots? The argument of an even root has to be what? What are the only numbers I could plug into an even root? Yeah, so it'd be non-negative numbers, right? So then we would just have to say for our domain, 4 minus x squared has to be greater than or equal to 0 and solve that, right? Does that make sense? Okay, which would mean that x squared has to be less than or equal to 4, right? So if I square root both sides, x, the absolute value of x would have to be less than or equal to 2, right? Because if I square root both sides, I'm actually getting the square root of x squared is the absolute value of x, right? Okay, so if the absolute value of x is less than or equal to 2, then that tells us that x is trapped between negative 2 and positive 2. So that's our domain. Okay, right? Does that make sense? Okay. So then we'd end up with just a different kind of domain that looks like that. And then from there on out, it's not very bad. Okay. We can continue with that one if we want to. We can, I'm not going to push it on you. There's another one. I mean, that's just one like we did yesterday, only instead of having a slant asymptote, it's got a horizontal asymptote, but otherwise it's very, very similar. It'd be 1, yep. Everybody get that? It'd be 1 because all I have to do is look at, and how do I know that? I could use L'Hopital's rule now, right? If I take a limit as x approaches infinity, I get infinity over infinity, so I could differentiate the top and the bottom. I don't even have to use the rules I used before, right? By L'Hopital's rule, if I differentiate, I'd get 2x over 2x, and then that simplifies to just 2 over 2, which is 1, right? Or the way we looked at it, I don't even have to do that. The way we looked at it, we know that it's always going to go as the ratio of the leading terms, which is 1 in the limit. Does that make sense? Okay. I look at the leading coefficients. 1 over 1 is 1. Yes, sir. So the vertical asymptotes would be where the denominator equals 0, which is nowhere in this case, right? And the numerator does not, right? Say it again. Okay, it only has to do with the limit if you need it to, right? Like the example we looked at yesterday was, I think, let's see, it's coming up, I believe. Okay, there's another one. Like, what's the horizontal asymptote going to be here? 0, right? Because the bottom is higher degree than the top, right? If I used L'Hopital's rule and took a limit as x approaches infinity, I would get 3 over 2x as x approaches infinity, which would be 3 over 0, which is infinite, right? Or sorry, which is 0, sorry, right? 3 over infinity, which is 0, okay? But again, I know I don't have to because I know my rule. Bottom degree is higher than the top. Okay, but again, that's not the one we did. Whoops, there's the one we did, okay? So with this one, we didn't need to take a limit. We didn't have to because we could see that the zeros of the denominator were 1 and -1. But when I evaluate the function at 1 and -1, I end up getting a number divided by 0, which is unambiguous. That's vertical asymptote, right? It's only if I get something that's indeterminate that I'd have to go further until I either get one of two things happening. Until I either get, if it's indeterminate, keep going, I'm either going to end up getting a over 0, which means it is a vertical asymptote, or the limit exists, in which case it was just a hole. Okay? Make sense? Okay. So that's the one we did. And that was a good example. I thought that one was, hopefully that one was pretty clear. And the video's up there. Here's the other one that I think wouldn't be terrible, just because it's an absolute value function. You got to make it into a piecewise function. Those are tough. I mean, they're just good to see because eventually you're going to battle those in college. And so it's nice to have some experience with them. And that one I think we could probably skip. Probably. I think we did one similar to that anyway. That's the other one. It's just got a trig function in it. And that was it. Those are the only ones I was thinking about. So you guys just tell me if and when you want to go through any of those. Yeah, I can't. And I'll tell you what I'll do. Like, I'll just go through it, and you don't have to pay attention. I'm going to record it, right? You can just kind of pay attention if you want to. So what about this one? I want to look at one thing on the example that we see on the test. Let me look at this real quick. Okay, yeah, they do limit the domain. So I'm going to treat this one that way too. There is one trig function on the test. I don't think it's this hard, personally. I will tell you it involves just sines and cosine. I'll even tell you it's a product of sines and cosines. I'll tell you that much. Okay. So this is even a little tougher because it's cotangent function. But let's just say we're going to impose a domain on this. Something like that. Okay. So then on our domain, 0 to 2 pi. Okay, well, yeah, are there any values we'd have to exclude? Yeah, right. Yeah, cotangent. Cotangent is cosine over sine. So unit circle, where is sine equal to 0? Yeah, it's going to be there and there, right? At the integer multiples of pi, because sine's a y-coordinate, right? So 0, pi, 2 pi. So we would have to exclude, so we'd really have to, our domain we'd have to kind of change this. It'd have to be from 0 to pi, excluding pi. So I'd have to exclude all those values, right? Those would be, and those would be vertical asymptotes, wouldn't they? Right? Those are zeros of sine, but not cosine. Okay. So if we made our table, well, actually we don't make a table yet. No horizontal asymptotes, obviously, right? We differentiate. So if I differentiate, I'm just going to get 2. What's the derivative of cotangent? Okay, good. And then y double prime would just be the derivative of negative cosecant squared would be, got to use chain rule, right? It's going to be a power first. So I'm going to get negative 2 cosecant x times the derivative of cosecant x, which is, go ahead. Say it again. Oh, no, we didn't. No, we'll do that. We'll do that in a second, yeah. Because cosecant squared is literally the quantity cosecant squared. So I've got the derivative of hand squared is 2 hand to the 1 times the derivative of cosecant is just negative cosecant cotangent, right? So our derivative then is equal to positive 2 cosecant squared x cotangent x, although we'd much rather write these in terms of sines and cosines, right? So what's that going to be in terms of sines and cosines? Y double prime would equal 2. Cosecant is 1 over sine. Cotangent is cosine over sine. So I'm going to get 2 cosine x over sine cubed, right? So again, that's going to equal, the derivative is going to be undefined only at the places that are not in our domain anyway, right? And how about this one up here, y prime? If I write that in terms of, it's undefined only at the places where the domain's undefined anyway. We could make the statement here instead about, how about if we do this? Y prime equals 0 when cosecant squared x equals 2, which would be the same thing as saying when sine squared x equals 1/2, right? Does that make sense? So then that's going to give us x equals plus or minus square root of 2 over 2, right? So where's that going to be? Well, we know those places. X is plus or minus square root of 2 over 2, well, that's going to be at there, 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 and there, isn't it? All those places, right? All those angles, okay? Sorry, when sine x, not when x. When sine x equals plus or minus square root of 2 over 2. So those are going to be at all four of those places. So those would be at x equals pi fourths, 3/4 pi, 5/4 pi, and 7/4 pi. Those would be my critical numbers for the first derivative, right? Second derivative, y double prime equals 0 when cosine x equals 0. Well, cosine equals 0 there and there, right? So that's going to be at x equals pi halves, 3/2 pi. Okay, so now we could add all this stuff to our table. Oops. Oops. Right, functions undefined at all those places. We had first derivative critical numbers at pi fourths, 3/4 pi, 5/4 pi, 7/4 pi. Second derivative critical numbers there. So this actually works out pretty well. We can test the signs of the second derivative at each of the first derivative critical numbers, which is going to tell us what these are, and it's going to determine whether those are points of inflection. So this thing works out great in that sense. Right? Everybody see that? So everybody that's watching, you don't have to watch. So if this is our second derivative, that'd be a convenient way to look at it. Cosine over sine cubed. So what's the sine of that going to be at pi fourths? Well, at pi fourths, cosine is positive and sine is positive. So the second derivative is positive. What about 3/4 pi? That's quadrant 2. Cosine is negative, sine is positive. Negative, right? What about 5/4 pi? That's quadrant 3. Both are negative, and sine is being cubed, right? So that makes negative over negative, which is positive. And then at 7/4, that's quadrant 4. Cosine's positive, sine is negative. So we get a negative overall second derivative. And look what that tells us. We get everything we need right there, right? We get minimum, maximum, minimum, maximum, inflection point, vertical asymptotes. Boom. We got it. What about symmetry? If we want to check symmetry, we would just do our test for symmetry right up there. Okay, so 2x plus cotangent x, let's do that at the bottom. Okay, let's evaluate this at negative x. So that's going to give me negative 2x. Cosine of negative x is the same thing as cosine of positive x, right? Think unit circle. If that's x and that's negative x, the cosine's the same for both of them, right? So I'm going to get plus cosine x. What about sine? Sine of negative x is opposite of sine of positive x, right? So this is going to give me negative 2x minus cosine x over sine x, which is negative x plus cotangent x, which is negative f of x. So it's odd. Okay. Say it again. Yeah, 2x. Whoops. You're right. Mm-hmm. Yep. Okay. And that's everything we would need to graph this thing pretty easily, right? If we wanted to graph that, let's just do that real quick to sketch this thing. I didn't plug any points in. Should we do that? I mean, we certainly, I mean, it would be easy for us to plug values in if we wanted to. I'm not going to do that. Oh, that was the end. Huh. Yes, rotational symmetry about the origin. Yeah. Does that make sense? Okay. So, what's this guy going to look like? We're going to get... that's 0. Okay. Oh, but the symmetry doesn't even help us here, does it? Because we're going from 0 to 2 pi anyway. So the symmetry is irrelevant. They wouldn't ask you about symmetry in a question like this. Let's see. Okay, this one's going to be, it is going to be odd, because look, you're going to get, you have an odd function times an even function is an odd function. So it is odd. It's never about, odd symmetry is always about the origin. That's the definition of odd symmetry. What? Do it again. Let's see. Oh, consider the domain of the function. So what's that mean? Yeah, that's, what the heck is that? Because, okay, I see why they're doing this. That's kind of dumb. It's because of the domain goes from 0 to pi. So in the domain, it's not going to have any symmetry, because the symmetry would only exist if you had a domain that was symmetrical about the origin, right? See what I'm saying? There is no, that's pretty dumb. That's a silly question. I'll make sure those are not on the test. You see why you see why they're saying no on that? Exactly. Yeah, it's not. Now, if the domain had gone from negative pi to pi, then you could have symmetry because your graph would be reflected or rotated about it, but you can't rotate it because in this case, that's not part of the domain of the graph. So you can't have any symmetry because symmetry, the domain doesn't allow it. Yeah. Question? Yeah. Okay. Minus. Well, that looks right, but you're not done.
Yeah, I know. I just don't know how to go on.
Okay, so then what would you do here? Look what you can do. You can factor some stuff out, first of all. You could factor out an x squared plus 1 and cancel it with the bottom,
Okay.
right? That would help. Then you'd end up with one of them there. That one's gone. See what I'm saying?
Yes.
And then you could even, if you wanted to, like factor out a 4x or something too, if you want to. Although at that point, you could, I mean, you could either do it now or you could just distribute everything and then factor out a greatest common factor. Does that make sense?
Yeah.
Okay. Okay. So if anybody, Max, do you want to see how this looks? If we could sketch it. Okay, so then what's that tell us? We're going to have vertical asymptotes there, whoops, there, and there, and there. And we're going to have, our function's going to do, we've got a minimum, an inflection point, and a maximum. Yeah, so it's going to go like this, right? It's going to go something like that. We'd have to plug in some values to see where those peaks and valleys are, right? But there's my inflection point, there's my minimum, there's my maximum, and it's just going to do the same thing over and over. It's just going to repeat, right? It might be stacked up when they get taller or something. Again, we'd have to plug in some values just to kind of see where those things are if we want to locate them. But this is the shape. Okay, that makes sense. Mm-hmm. What's that? Oh, previous page. Like yellow or green, or what are we looking at? Yeah, that just goes from here, right? Because cosecant is 1 over sine, so that's going to be, at this point, we've got 2 over sine squared times cosine over sine gives us 2 cosine over sine cubed. Cosine over sine. See what I'm saying? So this is giving us a sine squared in the denominator. That's giving us a cosine in the numerator and a sine in the denominator. And we're looking at a product of those. Yep. Okay, I'm going to turn this thing off.